a little bit trickier. Yeah. So we'll be careful with A6. You've got 3 charges, 4 microcoulomb, 2 microcoulombs, 2 microcoulombs, and each one of them produces a field. So here the field is going out, and here the field is going out, and here the field is going out. Okay, so the first question is, what is the electric field strength at the center of the circle, right here, due to the top one? So if you're just looking at the top one, what is the electric field strength? So if you remember the formula for electric field strength, yeah, K times Q over R squared, isn't it? Yeah. That's the electric field strength. So, okay, let's type that in. No, is it given? It's, yeah, the R is given as 4.33 times 10 to the minus 2 meters. Right. The Q is 4 micro, and the radius squared is 4.33 times 10 to the power of minus 2. So I got an electric field strength, quite a large electric field strength actually, 1917456 newtons per coulomb. So we'll want to maybe put that in megas or something. Yeah, we could go with 19.2 mega newtons per coulomb, 10 to the 6. Okay, which is fine. Yep. Now the next part is the really tricky part. Huh? Oh, I'll have to get it up on the calculator, but it should be in the formula book at the front.
1 over 4 pi.
Yeah, it's 8. Yeah, but it's also here 8.99 times 10 to the 9. Look under Coulomb's law constant on the front page, okay? Right, 2. Determine the resultant electric field strength at the center of the circle, including its direction due to all 3 charges. Okay. Can I go down?
Yes.
There's a second part. Now, to make our life a little bit easier, I'm going to calculate the electric field strength for these. Since they're both 2, it'll be the same. In fact, it's the same calculation except for one difference. What's the only difference between the bottom 2 and the top 2? The charge is half. So in fact the electric field strength is half. Yep, exactly. So I'll write E2 to represent the electric field strength due to the 2, and that'll be 9.59 meganewtons per coulomb. And E4 due to the top one. Yeah.
What? If we just put the number don't show the calculations.
Like how I just did?
Yeah.
Yeah. Well, I suppose in the exam you'd have to at least do something like this, and then that's fine. In fact, when I look at the marking scheme now, I can see that's what they did. So you could do something like this, yeah. I wouldn't expect you to recalculate it since it's almost the same. Anyways, what you have now is
E3 or
E4. E4. I'm just calling E4 as in for the number, the charge.
Okay.
Yeah. So you have 3 force electric fields at the center. One going up, one going left. No. Yeah, the electric field, sorry, the electric field is going down. So which way is the force? Well, it doesn't actually say. In the diagram in the marking scheme, they have the arrows going the other way, but electric field is positive to negative. So these are positives, yeah, so they're coming outwards, not going in. So you have an electric field from the top, an electric field from the bottom, an electric field from the bottom, like this. Okay. So can you see what I did there? I drew the tree in. Now, think about it like this. These electric fields, they're not going to work together. For example, if I put a charge here, let's say I put a positive charge here. Or let's make it even easier. I'll put a negative charge in the center. Where will the negative charge want to move? Well, the 4 is pulling it up, isn't it? But the 2s are also pulling it down as well. So my point is these electric fields aren't going to work together. What's going to happen is, well, yeah. So like if I break this up into a horizontal and a vertical, a horizontal and a vertical, I don't care about these horizontal parts because they're the same. They'll cancel. So I know for a fact that the electron will not move left or right because horizontally it's the same electric field strength. So at most it will either move up or down.
Maybe because if 2 or 4 is equal, so it should stay in the middle.
It could also stay in the middle if they were equal as well, yeah.
They're equal.
No, but they're not in the same position. I feel like...
The diagram is like,
No, I can see the diagram here. They're not in this... What do you mean? They're not equally apart?
yeah.
But the question says they are. They're 120 degrees apart. It means this here is a perfect equilateral triangle. Is that what you're saying?
So it would stay in the middle. Because
No. Because I think it will... The electric field on the top will be stronger than the 2 at the bottom. Because the 2 on the bottom, they're wasting some of their electric field strength by competing horizontally. I suspect that these 2 verticals will be less than this vertical. So the result is there should be a downward electric field. This electric field, how big was this one?
1, 4.
It was 19.2, yeah, meganewtons per coulomb. These ones here, what's this angle, do you know?
160.
It'd be 60, yeah. Half of 120. So this upward component here would be 19.59 cos or sine 60? Sine 60. How many of them are there though? 2. And again it would be meganewtons per coulomb. So just to be clear with your geometry, each of these is 120. No, sorry. What am I saying? Each of these are 60. It's an equilateral triangle. Right, so let's see what we get for the downward part. That's it multiplied 2 as well. So it multiplies 2, so it goes back to being 19.2 meganewtons. So I just need to multiply this by sine 60. And here I get 16.6 meganewton coulombs. So these 2 will cancel each other out, and in result there'll be a downward electric field of 2.59 meganewtons per coulomb.
Minus 19.
Yeah. which is not the answer.
How did you do?
Their answer is 9.59 mega.
Oh.
Am I in radian mode? No, that would be embarrassing. Okay. Horizontal components of EC and EB will cancel out. That's what we did. So you're just left with EA. Some of the vertical components. Some of the vertical components will be 2 times 9.592 times 10 to the 6th, acting vertically. Yeah.
The answer is what?
Huh?
9.61.
Are you?
What are you saying?
9.61.
I typed it in wrong in my calculator.
No, I put the sign as a 30 degree.
30, and that's right.
Because when you make a line in vertical, this angle should be 60, and
Yeah.
this is
Okay, yeah.
90, and this should be 30.
So you're saying that this here, you use 30 instead of 60?
No, just 60 or
This is not 60. This is 30. I know this. I know this. Don't worry. I know this.
I often
Huh?
Can you use
The- You signed 30? But why? Why sine 30? Why not cos 30 if you're going to use 30?
9.59?
Do you know what I mean? Why what did you type in?
just change the 60 to 30.
But why?
What's
You can't just, why would you just change it to 30? Why? No, but tell me, I want to know why. Is that not the vertical component?
When I drew like this,
Alright,
this should be 120, and this should be 60, and this should be 20.
thank you.
Correct?
Maybe. And by maybe I mean probably. Oh, that's terrible of me. Terrible. Sorry, the force is not going this way. Why not? It's going to the
Horizontal.
center. That's why the 60 is wrong. Because the 60 is pointing up too much. It's going to the middle. Yeah. It's 30.
Okay, half of 60.
Yeah. Oh, that's embarrassing. Alright.
Is it correct?
Well, let's see, Tacken. Goodness. I want coffee.
9.59.
9.6.
Yeah, it's 9.5. Well, depending on how many decimal places, but you actually get 9.59. So when you do 19.2 minus this, you get the correct answer. 9.59. Wah, wah. Wah, wah, wah. Let's go back.
Taking him on a roll.
Huh?
Taking him on the
He's on a roll. He's the only one doing revision, I think. Mega newtons per coulomb. So the electric field strength, it'll be going down, and it'll be 19.2 meganewtons coulombs minus this, which was 9.59 meganewtons per coulomb. So the answer is 19.2 meganewtons per coulomb downwards.
19.
9. 9. The heck? 9.59 meganewtons per coulomb down.
Do you have coffee now?
I had no coffee this morning. I think this is the main culprit. Right, 7 now.